Hi guys, this video is the second part of our fourth live session on the SoccerNet-v2 challenge. We were happy to welcome Bastien Vanderplaetse, who presented his action spotting method relying on both audio and video.
Don't forget to join us for our next session on Thursday, the 20th of May at 2 p.m. UTC. We will have a first talk by Kamal from the University of Waterloo on his multi-term CNN method for action spotting, and a second talk by our colleague Meisam regarding our replay grounding benchmark. This will also be your chance to ask questions or discuss ideas. All the links are in the description below. Don't forget to subscribe to this channel to support us, and enjoy!
Bastien Vanderplaetse received a master's degree in computer science at the University of Mons in Belgium, and he is a PhD student at the ISIA lab of that same university since October 2019. His work focuses on audio processing, which he coupled with video analysis in his work about SoccerNet, published at CV Sports last year, which he will now present to you.
I will present you the paper that was published at CV Sport last year, which concerns the improvement of soccer action spotting using both audio and video streams. We mainly focused on two tasks, the soccer action classification and the soccer action spotting by using the SoccerNet dataset, the first version. Our analysis of the audio stream was due to the fact that our intuition led us to think that adding the audio stream to the video as input should increase the performance on both tasks, but it should also provide some useful information about the action through sound events. For example, the fan will generally shout out when a goal is scored, or they can show discontent at red cards. For the video representation, we use the work provided by Silvio Giancola, who was the author of the original SoccerNet dataset. All the videos are unified at 25 frames per second and are trimmed at the start of the game. For each video, frames are sampled at 2 frames per second, and these sampled frames are resized and cropped at a square resolution of 224. The ResNet 152 pre-trained on the ImageNet dataset was used to extract the video features. We used the output of the last hidden layer, which is a layer giving 248 dimensional vector for each frame. And finally, PCA was applied to reduce the features at a dimension of 512. For the audio representation, we used a similar process. We start by trimming the audio stream at the start of the game, and we divide this stream into half-second size consecutive chunks. Each chunk is used as input to VGG-ish, which is a deep convolutional network architecture pre-trained on AudioSet. AudioSet is a benchmark dataset which contains more than 600 audio event categories and more than 1 million labeled 10-second audio segments. More specifically, we extracted the output from the last convolutional layer of VGG-ish. And finally, we applied a global average pooling to get features vector with the same dimension than the video features. The general approach we use is the same than Silvio Giancola. We use his approach in order to test the benefits of the addition of audio streams. This process starts by training a model on the action classification task. As explained before, the sample frames of the video stream are used as input for a ResNet to get video features. These features are divided into successive windows of a certain duration. Here the duration is t seconds, and so we have chunks of 2t times 512 dimensional window. And finally, those chunks here are given to a multilabel classifier. This classifier is multilabel because there are windows that can contain several actions that are temporally close by. Then the architecture will use a sigmoid activation function on its last layer. And for all the classes, we use a multi-binary cross-entropy loss, which is minimized. The optimizer that was used is Adam, and the learning rate follow a step decay and an early stopping. Next, for the action spotting, we have instead of dividing the video into successive chunks, we use a sliding windows of t seconds with a stride of 1 second. For each position of this window, we have a two-dimensional matrix of dimensions 2t times 512. This matrix is used as input for the trained classifier. Then for each game, we have a series of predictions about the different labels. And to obtain the final spotting candidate from this prediction series, 3 methods were used. The first apply the non-maximum suppression within the window and select the local maxima along the video. And the two others use segment proposals with a watershed segment. One selects the center time within the proposals, and the other selects the time index of the maximum value. Now I will talk about the multilabel classifier and how we use it to realize multimodal fusion between video and audio streams. The baseline proposed by Silvio Giancola used the video features as input of a pooling layer. Next to this pooling layer, we have a dropout with a key probability of 0.6. And finally, the classification is done by using a fully connected layer, which gives us the logits. And thanks to a sigmoid activation function, we get the probability to belong to each one of this class. To add the audio stream, we duplicated this model and we replaced the video features by the audio features. At different steps on this pipeline, we have merged both streams. For example, we have the first method was at the end. So we have the video features that goes through the up part of the pipeline and the audio features that goes through the down part. And the results are merged at the end of the pipeline. For the next two methods, we merge at the logits. And after this merge here, we have only one sigmoid function that is applied to this to the merge result. And we tried at different steps before the fully connected, before the dropout, and before the pooling layer. So we have 5 merge points and 7 methods. As pooling layer, net-or-vlad and net-vlad were used, which are clustering-based aggregation techniques. And these models harness context gating, which is a learnable nonlinear unit aiming to model the interdependencies among the network activations. For our experiment in video chunk classification, we used the mean average precision. The model we used was this is a model which provided the best result in Silvio Giancola's paper, which was net-vlad with 512 clusters. But this high number of clusters have a high computation load. And so we use net-or-vlad with k equals at 64 clusters to find the best merging methods. And here are our different results. The video baseline row corresponds to the result by using only the video stream. The audio baseline is just by using the audio stream. And the 7 other rows correspond to the model using our different merging methods. We can observe that by using windows of 60 seconds provide better results than the 30 seconds windows. This can be explained by the fact that with 30-second video chain, the background class represents more than 93% of the training set. And for the 60 seconds video chain, this class is only 87% of the training set. Since there are more samples in the background class, the 30-second based models tend to classify more examples with these labels, which reduce performances. Another observation is that the audio stream alone will provide inferior result than using only the video stream. But the best performance are obtained by the forced merging method, which corresponds to the merge point localized between the dropout and the fully connected layer. And with this model, we have a precision of about 73%. On this table, we show the performances on the different classes of the dataset for this best model on video classification. The multimodal model, which is the last column, provide a better result on all classes. The audio model is the worst in terms of general performance and is also the worst on all classes except for the goals where it is better than video baseline. The audio stream seems also to carry some information about substitution, which can be explained by the fact that the fans can upload or boo a player according to his performance on the field. But the cards seems to be not well detected by the audio stream. Now that we have determined the best merging method, we have trained the models using the NetVLAD with 512 clusters as pooling layer. And we compare the result for the video-only model, the audio-only model, and the multimodal model, each one with 2 window sizes, 60 seconds and 20 seconds. Our observations are still the same. Bigger video chunks provide better result, and using only the audio provide the worst result, and the multimodal is the best one. In average, the MAP has increased by a bit more than 7% by adding the audio as input. Now that we have determined the best model, we can evaluate them on the action spotting task. And for this task, we introduce the parameter delta, which is the tolerance in the precise time instant of the detected event. We also use the average MAP, which is the area under the curve as a function of the tolerance delta ranging from 5 to 60 seconds. And we evaluated 3 types of model in action spotting task. The one using the net or VLAD with 64 clusters and 60-second windows, the NetVLAD with 512 clusters, and both with 60 seconds and 20 seconds. This table shows all our results for the action spotting. As before, we can see that using only the audio performs worst and that the multimodal approach is better than the monomodal ones. The best performances are obtained by using the center time watershed segment. However, this time, the smaller chunk size performs better. We can explain that by the fact that model streams with 60 seconds video chunks will have decreasing performances when the tolerance delta becomes lower than 60 seconds. However, if model streams on 20 seconds video chunks perform well with a tolerance of 20 seconds, it will still be efficient for higher values of delta. And finally, we can see that in average, adding the audio stream as input increases the average MAP by a bit more than 4%. To conclude, we have studied the influence of audio stream on two tasks, the action classification and the action splitting. We have seen that using only audio stream is worse, except for the goal class. Using a multimodal approach based on both video and audio streams seems to improve the performance on the SoccerNet dataset. We get better results for every class, and it increased the performance on both tasks by more than 7% for action classification and more than 4% for the action splitting. And we have also observed that smaller video chunk sizes perform worse for action classification, but better for action splitting. Another study that can be followed by this one is that we can study what is the most influent part of the audio. Is that the ambience in the stad or the commentator, which can be more excited when the game becomes more interesting. That's all for this. Thank you for your attention. And you have here the GitHub containing the source code of this paper.
That's great. So thank you very much to our speakers. So as we've seen, there are some very interesting insights to get from those presentations. So for example, Bastien showed that using the sound can be very easy somehow and very useful too. So probably that can be another part of your own works. So hopefully someone will get very good results by merging all those ideas, and we will have very interesting submissions in the future weeks. So thank you very much for attending this presentation. Of course, we are going to post it on YouTube as usual. And good luck for the challenge. There are 3 weeks left, 3 weeks remaining approximately. So if you have any question, reach us or go to Discord and ask your questions on Discord. There's no problem. We will try our best to answer them. So thank you very much and have a good day.
Bye.
Bye.